one of the most important courses, especially nowadays. If we are looking to anything around us, you will find lots of application in power electronics. So power electronics, for example, if I'm looking to this one here, what's this? It's computer adapter, right? So if we look at this computer adapter, our input source is 214 Oman standard and 50 Hz, right? AC. However, my laptop, the voltage on its terminal, you can see it's about 20 volt. So how I can reach from here to here? I have here an AC form. However, here this 20 volt is a DC form. There is some stages between this one in order to reach to that one. And this is what we call them electronics or power electronic circuits. And there are different types of circuits. For example, what we can see from here, I have an AC and here I need a DC. So I can use AC circuit and convert it to DC circuit. Okay? How I can do this one? Have you heard about rectifier before? Yes, to those who study electrical, they have heard about that one. So the circuit which is here, I can summarize it. First of all, it will be stepped down through a transformer, and then after that, it will use a diode bridge. This diode bridge, I will talk about it tomorrow, inshallah. So this bridge here, what exactly do? It transfer this AC from this side, this one step it down the voltage, and then transfer it to lower value, and then to fit the 20 volt. Here there is something like filter and regulation added to keep the voltage 20 volt, which should be supplied to this circuit. So this is like one example of power electronics. Now if I ask you a question, can you define power electronics by yourself? What is power electronics? Look at here, I have this one and I have that one, which is AC, and then I have DC. Can you define power electronics? What do we mean by power electronics? This is one application only. But also, go ahead.
Devices that can change the power to different types. Change from AC to DC.
Okay, great. And
Change the power from state to state. No.
yeah, this is good also, the same thing. So, is there any definition or something like that you'd like to say? Yes. Every device has specifications. Example, if you look at your mobile here, you need to charge this one with 5, it should be the voltage 5 DC, right? So you cannot charge it, for example, using that adapter, even if you change that small adapter here. This one is still 20 volt. Therefore, you need to fit the needs of that one. So you need to get here, if you are using mobile, you need to get another circuit here or something that can give you a DC of 5 volt and with some specific amount of current to charge this mobile, right? So that means every device has different ranges or specifications, and you need to meet the specification. Therefore, you need to control or to utilize those power sources in order to meet the required specification of your devices. So this is, we can define power electronics. Now, based on that one, power electronics can do lots of jobs. You will find rectifiers and we will talk about it tomorrow. Okay, and then you will find also if you have DC to DC. So many of you will ask me, if you have a DC, why you would like to change it to another DC? Exactly. Exactly. Suppose that you would like to charge your mobile from the from the car outlet, right? And that one you have it's 12 volt, right? So in that case, if you would like to charge your mobile, you need to step down the voltage from 5 volt DC, from 12 volt DC, which is the battery of the car, to 5 volt. That means this is one application of that. What else? Can I see an application about that? Do you have, or do you know any other application which is important for us? In terms of DC to DC. If we look at solar cells and the panels, normally the panels, the voltage across the panel is low, right? And you need the voltage. For example, if you would like to charge a battery, or if you would like to connect it to grid, or you would like to connect it to inverter, and then so you need to change this one to 12 volt DC. Can you hook directly your solar system directly to this one to charge that battery or to connect it to grid? No, because it has a fluctuated value of voltage. It changes with the time, right? Therefore, DC to DC chopper is important, so it can operate like buck, which is step down the voltage. So some circuit called buck circuit, they can step down the voltage. There is another circuit which is known as buck boost. Buck boost circuit, they can step it down and step up. In addition to that, there is another circuit which is boost circuit. So this is the three important types of circuit, and there is many different types of circuit inside that one. We will try to cover the basic one in order to understand what those circuits are doing. Actually, this one means step down, this one step up, and it can step up and step down the voltage, and this one's only step up the voltage. We will tackle this part during the third day. Okay. In addition to that, also you can get, if you have DC and you want to convert it to AC, which is inverter. It is known as inverter. So this type of circuits, suppose that, I can give you an example. After you charge the battery from solar system, you charge this battery through a circuit which is here, we will see after 2 days, and then you would like to inject this power or to change this power to an AC in order to utilize it for your any other application or whatever you can name. So you will have here this DC, you will change it by the way, if it is 12 volt, you need first to put another circuit which is like buck boost circuit or boost circuit in order to boost it up, and then hook it to the inverter. The inverter, what it will do, will change the DC to AC. This type of circuit, we will see it in the fourth day, the last day. And then after that, you can utilize this one. Now you can change it to what specification you need. For example, you can make it 240 and 50 hertz, and you can use it anyway. So this is the summary of the course, or what we're going to tackle. There is also some circuit like AC to DC to AC, And this one also it can be used in the wind. Wind turbines, they produce, when the turbines rotate, they produce AC, right? AC type of power, right? So this output, it's fluctuated, it's not constant, it changes. Then there is a type of wind, there's a type of wind, so bark, which is known as type 4, which is used the power electronics technology with this technique. They change it to DC, and then this DC again, it is converted to an AC, which is regulated one with the required value. And later on, it can be injected to the grid or used in domestic application or island application. So it depends. Any questions so far? Do you have any comment or anything you would like to say? Sharab, do you have any questions? So let's go through your slides. So during this lecture, I will cover introduction, definition. We discussed most of those now, and then why we need those, and then the multidisciplinary aspect of that application of our importance. If we look at this system, it's a drive system, or we can say this is a load system. And for example, if you would like to control the voltage or whatever there here, suppose we can assume that this computer or whatever there, and this block represents the power electronic device or a circuit. Now you have the input, which is 240 volts, and then you would like to get it like 20 volts here. But suppose that this load is changing or whatever here, and you want to keep this one constant, so you need a feedback loop, right? So what this loop is doing exactly, for example, it sends, for example, in this case, the voltage, and then compare it with the reference, and there's different types of controller can be applied, and the controller will try to create a signal that it change or control those circuits in order to get that 20. And this one is important. Suppose that you go to a place, you can even look at it like when you go to a place, you can see with different value of voltage. Suppose you go to standard with 110, like in Canada or Saudi Arabia or whatever, and the input voltage is different, right? Now, if you put that one directly, still you will get 20 volt. And why is that? Because it depends on the designer of the circuit, but normally if you look at it, it will sense the voltage directly, and then the reference will change that switching frequency of that one in order to get again 20 volt even if your input voltage changes. Okay, so this is, and the role of power electronics is, we discussed it about 5 minutes ago, and we said that it can make the energy or the power convenient to each devices depending on the specification of the device. And why we have seen the growth of power electronics right now? Because if you look at name whatever you hear, projectors, whatever computers, whatever you see, you need it, right? So you need power electronics to change from state to state depending on the device which you need it, and lots of devices you can find. If we look at this system actually it's a linear power supply. If we look at power electronics actually use switches like diodes, or we can name different types, switches like diodes or Transistor also, it can be different types, MOSFET, IGBT, and there is many types of switches in the market. You can get them easily. Now, if you look at those switches, for example, transistor here, it can be operated by in two mode of operation. It can be operated linearly, or it can be operated in saturation region. Okay, so it depends on the signal which you send it to that one. It can operate either in this mode or in the other mode. But in power electronics, we operate this one as a switches. So we send enough signal, either voltage or current, depending on the type of this transistor, and it is enough to turn it off completely or turn it off completely. But we are not working in linear mode. Linear mode, they use it in small application, or in where the current is low, like in electronics devices with milli of watts or milliamperes. They use those. But when you go to large application, no. We need to use switches or transistor as a switches to turn on or turn off. So if you look at a linear system, you can look at, for example, this is, and why is that? Let's look at a small system. Example, if I give you 10 volt here, okay, and then you have, for example, a load or a resistance of, let's assume it now, 2 ohm. If I ask you, I need 5 volt across this one, what shall I add to this circuit in order to get 5 volt? You can add a resistance, right? You can add resistance. This one. And what's the value of this resistance? 2 ohm. Exactly. If you put 2 ohm, you will get 5 volt there. But now, if you think about this one, can you tell me what's the current here? 10 divided by 4, right? So it will be 2.5 ampere. Okay. 2.5 ampere. So if I ask you, I need 5 to be honest. Okay, but this one, it consumes power, right? What's that power? It's B equal I B, or B equal
R square.
exactly I square R, right? So this one, it will be the power 2.5 square multiplied by 2. So I go right. If I'm looking to this battery will generate energy for this one and this one. So that means I'm losing energy here. My device is that one, I'm assuming, right? But now I'm losing power here, right? So that means it's not a good way in order to get the 5 volt by using that circuit. It's a linear circuit. The same thing. If I'm looking to a transistor like this, the same thing, 10 volt and 5. I need 5 volt across that one, and this is 2 ohm. If I'm trying to use this circuit linearly, like that one as a linear, okay, I will send here, if I'm assuming that a BGT1, if I assume it like this, definitely I need to send a gain or a current that can make the voltage here 5 volt. So I have to keep a current signal like this. The same thing. If you look at here, I will have 10 volt, right? And I have here 5 volt. According to the KVL, I will have between this point and this point 5 volt drop. So this 5 volt drop also creates losses. Now, what if I do another circuit like this as a switch? I will use the same transistors, but instead of sending the signal like this one, I will send it. I will operate this one in you can see in saturation region. That means I will send enough current to turn it on completely or turn it off completely. Not like this one. Now this one you can look at it like a tap like a controlled tab like this one of water, and you have a water here, right? And then you want the flow of water to specific value or something. You will press that one with a specific brush in order to get that water in this case. So in this case you will have some losses here, and in the case of power electronics where the current is high, it's not recommended because it creates lots of losses across the switch or the transistor itself. Therefore, what if we go to a circuit like this? The same circuit, instead, for example, if I make it to the first as a switch. By the way, this switch could be a transistor. Okay. Now, if I make it like so, I will have 10 volts here, and I need 5 volts here. Can anybody from here tell me how I can do that? Mechanical switch, I can turn it on and I can turn it off automatically, or you can look at it whatever you like. Just can anybody tell me how I can get 5 volts from that? Can you think? I have 10 and I have 5. How I can get 5? 5 from 10. ما تصل؟ Look, now, how I can get 5 volts from that one? This is the question. Anybody else? Yes, Sadalo? By high speed, but how I can reach to 5? Yeah, you need a high speed, yes. That's good. Yes, just let's look at it like this. If I'm looking to this circuit, if it is opened like this now, can you tell me what's the voltage across that resistance? 0, right? So now, that means if the switch is on, off, it is 0. What if the switch is on like this? On. So this is connected to here, and then you have a circuit like this. 10 volt, and then what's the voltage in this case? 10 volt. So now, based on these two circuits, I have two conditions, right? Either 10 volt or 0. So what if I make like this one? In a time like this, if I turn on this one for a while, okay, and then keep it off for the same value of time. For example, if I take it from here, from 0 to 0.1, example. Let's say second now, but later we can change, we can make it faster. Now it's very slow, you can see. 0.1 second, and then at 0.2 again turn it on, and so on. Look at here now. And repeat the same thing, right? So that it will be here 0.3 and here 0.4 second, right? And so on, right? Look at it now. Can you tell me what's the average? 5. Definitely 5. And you can find the average easily. This is one period, right? Mathematically, you can get it easily. You have it here, one period, right? And if you look at from here, from 0 to 0.1, this is the area, right? Which is 10 volts, right? In 0 to 0.1, and then from 0.1 to 0.2, 0. So if you get that average, the average can be obtained mathematically, which is 1 over a period. The period is 0.2, right? And the area under that period from 0 to 0.2, but from 0 to 0.1 there is 10 volt, right? And after that 0. So the integration only from 0 to 10 volt with only 10 volt dt, right? Sorry, from 0 to 0.1. Sorry for the type. D. So now if you just take this one, you just integrate it, you will get, you can take, this is constant, 10 over 0.2, right? And then t from 0 to 0.2, right? To 0.1, because this is the on time, right? So 0.1. And then if you go to that one, you will 10 multiply t, which is 0.1 minus 0, right, over 0.2. If you look at this one, you will get it 5 volts, right? Yeah. So if I apply like this, I will get like this voltage, right? But I need a 5 volt DC, not that one. This one, it's not AC actually, but it has ribbons, right? It has ribbons. Later on, you can even analyze that. You can see it's a kind of harmonics, okay, which is multiple frequency inside that one. Actually, you can analyze this one by Fourier series, and then you can see that one. There is another story behind this analysis. I don't think we can go through 4 days of course like that. So now, how we can do that one? Actually, if I have like those ribbons or output like that one, I can get like that one by designing So what the filter will do, filter those ribbons and will give me this average. So I can get the average purely DC by adding a filter on this side. So adding a filter here, example LC filter, so that means it will let the DC to pass through that one and absorb the other component, which is the AC. So I will get the average, which is 5 volt DC. So I can still get this 5 volt. Now, let's look at the switch here. Okay. I operate it either on and off, 2 cases, right? Either on and off. Let's see, is there any losses across the switch? In the previous, if you can remember here, in both types of circuit we have losses. There is a 5 volt multiplied by the value of the current here, losses. Here there is a loss, right? Now, if I'm going to look at it like this one, as a switch like that one, Let's look at to the first circuit and the second circuit. In the first circuit, is there any current passing through the switch? And what's the voltage across the switch? No. The voltage is 10 volt. 10 volt, B equal IB, right? I need to calculate the power across that switch. The voltage here exactly according to the KVL exactly equal that one because there is no voltage drop across that one. So definitely the voltage here is 10. What about the current? 0. Therefore, 0 by the value of that voltage, so it will be 0 by 10. So definitely 0 watt here. Right? Let's look at that one. Here. What's the voltage across if it is on like this?
0.
So the voltage is 0. Sorry. What about the current? 10 over 10, which is 1 ampere, right? So if you would like to calculate the power, it will be 1 by 0. 0 watt. So this one is consuming 0, and this one is 0. So did I lose anything on the switch itself? That means I'm utilizing my energy or my power efficiently, right? Just I'm supplying this load with 5 volt without. We cannot actually practically nothing can we say. You can say it's no losses. There will be a leakage current, definitely there will be some leakage, and there will be some losses, but it doesn't reach to that extent like those circuits with high losses. Okay, it can be high losses with higher load application. We mean by those systems. So remember, power electronics operate in two main modes using switches like transistors, diode, and there is another one which is thyristor for large application. So this is what we discussed right now. We give an examples, switch mode power supply, one of those devices, and then we discussed like that one. So for example, here you will have the utility power supply like 240, and then make a diode rectifier like this one in order to rectify that one, change it to DC, and then after that add a filter to filter that one, and then use the process depending on what you load type, and then regulate this value to get a specific value of voltage. And we discussed this one here on the slide about basic principle of switches, why we need the switches. The same example we discussed it now, approximate that one here. So this is just approximate the same example. If you look at that switch, it can be operated on those modes, and then there is a filter like that one. We can add it later. We will see. If you analyze those one, definitely you will find some harmonics or components. For example, you will find this is what is known the fundamental, and then there is some harmonics component. If we have time, we can discuss it later, or you can ask me during by the end of that lecture later on if you would like to know what's those. Constant. So constant switching frequency for the pulse, and pulse with control of the average voltage, and also the LC filter. If you look at this one, you can do that one using those. So you can send constant pulses in order to get specific value if you have constant voltage. But if this voltage is changing, you can get 5 volt by changing the period of that pulsing. So for example, if this one dropped to, for example, to 9 volt, it doesn't mean that you cannot get 5. You still get 5 by just increasing a little bit the period of on, and then decrease the time of off, and you will get still the average of 5. So we discussed what's power electronics is to control and convert of the electrical power from one form to another by means of power semiconductor devices like switches, like transistors, diodes, and other things. And it is used to process and control the flow of electric power from supply by supply voltage and current informed that is optimally suited the application of the device. Example, the phone needs 5 volts with specific value of milliamperes, you have to supply that. This one needs specific voltage, you have to do that. So this is how you can. So the rapid growth of this one is due to the advancement. One is the advancement in the power semiconductor switches. If you talk about 100 years ago, you cannot say power electronics, it's there. But now, the revolution since the thyristor invention, which is in 1948 until now, there is a lot of tremendous, and then IGBT and then the other, BGT and then MOSFETs and then IGBT, you will find lots of power electronics devices. I will try to bring tomorrow some of those to show it to you. Also, if we look at the microelectronics, including the microprocessor and microcontroller, because we need to switch on and switch off those. So there is no nowadays advances on that one. And now you can, even if you are interested in electronics, you can do those switches with different techniques instead of only analog one. You can do it with microcontrollers. You can do it now with DSPs. You can design your system, and even that you can interface it to your computer. And you can, for example, operate the circuit of the controller through the MATLAB through a data acquisition part, and then take those signals from the MATLAB, from the computer, send it to the switch, turn it on and turn it off, and then you can operate it. So many techniques. New control algorithm, you can find lots of, you can name fuzzy logics and so on. Demand of new application driven by the current and the contemporary issues. Now you know that now the renewable energy, and also when there is very important application, and you can see in the petroleum sector. When we look at the variable speed drive, you know this one, right? Have you heard about variable speed drive? ESPs, electrical submersible pumps. Actually, in Oman, how do they produce oil? There's two ways, right? Either beam pump, right? Or by using ESPs, electrical submersible pumps. Electrical submersible pumps, it can be controlled by two ways: variable speed drive or FSD, fixed speed drive. So if you go to BDO in different places, there is different types of variable speed or ESPs. But ESP exactly they do. Near the well where they would like to produce the oil, you will see a chamber. In this chamber, there is a power electronics devices. What they can do, they take the supply from the main grid, and then they put a transformer to step it down. So there is a transformer here, step down transformer. And then from that one, they connected to power electronics devices. Okay, it can be 6 pulse, like what they dominantly use in BDO, or it can be even 18 pulses or 12 pulses, it depends. What's inside that one? It it is just switches of power electronics. We will try to show you by the next lectures. And after that, again, it's step it down. After this, step it, or just change it to the required value, which is send the cables directly will be sent to the pump, which is located, it depends where the oil is located. So this is a pump here, which is electrical submersible pump. يقول in Arabic الغطاس اللي نازل تحت. Okay. So what it do? It suck that oil, but you can use this technique in order you can control the speed of this motor. Okay. Mostly, it's induction type of motor. They cannot use DC because this is not recommended in the oil areas where DC can explode and make sparks. Exactly. So induction motor. So induction motor, it can be controlled with different technique. It can be controlled by changing the speed, by changing the frequency or the terminal voltage. It depends. So this is one of the application which is used on the oil. The contemporary issue about power electronics, which is energy scenario, and this is important. Nowadays you can see that the oil is fluctuating, right? Why we don't tap on renewable energy? Why don't we utilize those? It's a gift from Allah. We can use it anytime. It's there. So we need to reduce the dependence of fossil fuels, such as coal, gas, you can name it. And also those fossil fuels, they will deplete after a while, right? We cannot rely on them. So renewable energy resources like solar, wind, fuels, and ocean, we can name it. It's our future, especially for us. If we look at Oman, solar and wind, right? Energy efficiency and saving by power application. For example, in variable speed compressor or air condition, about 30% saving compared to using thermostat. So this is why we need power electronics. In lighting, using electronics ballast boost efficiency by loss and flame to 20%. Therefore, good to use power electronics. From the environmental side, I don't know what time shall we stop at 8, right? So still we have half an hour. So I will try to rush it a bit in order. We have about 7 minutes video to show that it's good at least. So this is the environmental. You can see in different places. Also, if you look at nuclear safety and plants, they produce radioactive materials and they can make pollution. Burning fossil fuels also it can pollute and create global warming. And the possible solution, especially for us, renewable energy resources, also centralization of power station to remote non-urban areas to mitigate our area mitigation. So that means we can allocate different power sources or renewable energy sources in different places in order to utilize the energy. Also, electric vehicle, it's a good chance for the future if we try to use electric vehicles. We can utilize like renewable energy, and then instead of using fossil fuels. But if we look at the power electronics itself, it has interdisciplinary field. I cannot say that power electronics itself it can do the job. Definitely, power electronics circuit use switches, but also it needs to be controlled, and it needs processor, and it needs input and output. So it needs many things. So It need, for example, here, control circuit. It could be digital, it could be analog, and it will also power equipment. Could be static or rotating. This one is static, it doesn't move. But if you are controlling like motors, that means it's rotating, right? So definitely you need those, and electronic circuits, definitely. So those are the important field which is required to apply a device using power electronics. Digital analog electronics, power and energy, microelectronics, control system, computer and simulation. Computer and simulation also one of the important tasks for designing those. Because if you would like to design a device, at least you can test it before you start applying it or start the application. So you can see the output, everything by using simulation. By the way, I will try to use two software if I have time. I will use BSIM. BSIM, I will show you how to use that one, which is simple and we can simulate simple circuit faster. I will use demo one because it's enough for this course, but if you need, you can buy later. You can buy it from the market. Also, I will use MATLAB sometimes to show some examples. MATLAB Simulink. And also from the physics side, the solid state device itself, transistor, the development of those, also under that field of interdisciplinary field for power electronics, packaging of those devices, and also heat transfer. You can, if you look at the computer, or you will see that there's a heat transfer system on it. For example, you will see wind or whatever. So you will see that it has a fan or any device of that cooler system on those type of circuits. The application, you can find the application in different places, from the space to the ground and to the sea, different application. You can name it in the residential, commercial, transportation, and the next slide give you that one. So the applications in space, you will find power electronics there in the satellite, in Mars, over space stations, airplanes, you name of devices. In the sea, in different places, boats, ships, submarines, and in the ground, you can see in the electric vehicles, escalators, whatever you name it. Okay, so many applications of power electronics, and even in robotics application. In the oil field, oil industry, you can find lots of applications, especially to control the motors, and also for the fluid pumps. And at home, you can name lots of devices. Example, this one, you need to control the speed, how to spin, how to rotate that one. So it's there. And in those applications. This is in oil, like electrical submersible pump. This is where the power electronics device like VSD. Sorry about this. VSD is located here, or FSD is located here. It's a power electronics circuit. It can control the production of the oil through a cable and then toward the submersible pump, which is injected down there. So this is one application in the oil field. Also in mining and digging to control those pits. And now this is the circuit which we discussed during the first part of this lecture when we talk about if you have a DC and you want to convert it to an AC, you can do it through converter and through power electronic devices. So if either you have even clean or distorted, you can get an AC. This AC also, you can change it to whatever you like. You can keep it as a single phase, 2 phase, or 3 phase, or even you can increase it to 5 phase, or you can leave. So depending on your design. The same thing, DC to DC converter, it changed the DC to another value of DC. It could be step up, step down, or it could be all the device. It can work in both step up and step down. And even if it is distorted, we can convert it to that type of DC output. Any questions about? For the rectifiers, if we have AC, either single phase, 2 phases, or 3 phases, you can convert it to DC with such circuits. And also, if you look at here, if you have an AC and 1 phase, 2 phase, or 3 phase, and you want to convert it to another AC, you can do it. So you have the choice depending on your design or your device. So you can get whatever you like from this, but just by using the specific circuits. I think you have heard about this one, right? Uninterruptible power supply. Can you name an application that uses uninterruptible power supply to it?
Security systems.
Good. Yeah. This is the security system. Can you mention like some example? ATM machine. Okay. In surgery rooms where they to make an operation, they need that one. And why do they need that one? Because nobody can, for example, in the operation or any surgery, nobody can guarantee there is no disturbance on the grid, right? And it's very, very critical. You can see it's a critical issue that you need the power to be on, to power the device and to complete the operation, right? So this one is so important. How this one it will work? Actually, if you look at here, you have this source, right? Then what this source, this is the main source. What it exactly do? It convert AC to DC. In the middle, there is a backup, which is a battery. It stores the energy here. Okay? And some energy goes again AC to DC. Okay? And then supply that load. Suppose that this is a surgery room, which is here. During the normal operation of the grid, the energy from here, it flows through that circuit and then charge the battery if needed and then continue to that side. According to any disturbance or anything occur in the line, and suppose this one, switch it off, okay? What will happen? Now the battery will take this, and even nobody inside the room will sense that the power switch it off. Directly this one will take place, and this battery will supply directly the room or the operation room, and everything there, nobody will feel, everything stable, and they can do their operation and they continue without any problem. In the bank, you cannot rely, for example, if there is a storm and the power shut down and you insert your card inside the machine and you will lose your transaction, right? But if there is that one, even what happened there outside, you still can continue the process of transaction or taking your money from the machine. Any questions so far? Do you have any questions about? Are you okay? How we can do this one? Actually, when we look at to the control, we need sensors. You cannot design like a loop or something in order to control power electronics, okay, unless you have sensor. For example, if you would like to control the voltage, you need to sense the voltage and then send the feedback loop to the system and then control those switches, okay. So you need some sensors, so it depends what kind of control you would like to do. So it could be temperature, it could be pressure, it could be whatever. You will see it later in the next lectures. Now for the next time, I will just show you a video.
One of the biggest challenges of the 21st century lies in the transition to sustainable energy sources, moving away from climate-damaging fossil energy sources to the widely spread use of solar energy. Solar energy is harvested through many renewable energy sources such as photovoltaic, solar thermal energy, wind power, and hydropower. For example, the electricity demands for Europe could be met from a mere 0.2% of the total area of the Sahara Desert. The technology of solar thermal power plants that heat up a fluid using parabolic reflectors and thereby convert thermal energy to electrical energy by means of a generator is already available. One technical challenge lies in transporting the electrical energy to consumers in Europe, and the solution lies in power electronics. High voltage direct current transmission, abbreviated to HVDC, enables the transfer of electricity over many thousands of kilometers with high efficiency. With photovoltaic systems, solar energy can be directly converted into electrical current in semiconductor solar cells. In order to feed the DC current from the PV modules into the public energy supply network, it must first be converted into the standard 50 Hz AC current in a solar converter. High conversion efficiencies are crucial. The best PV converters with silicon carbide power semiconductors achieve over 98% efficiency. Wind parks are a common sight along the windy coastal regions nowadays. A country such as Denmark produces approximately 20% of its electricity needed from wind power. Power electronics also plays a key role in feeding the wind power into the electricity grid. The voltage and frequency of the electrical energy produced by these parks must be adapted to suit the transmission network. Due to the fact that the potential for the use of onshore wind power is already exhausted in several of Europe's coastal regions, more and more offshore wind parks are being installed at sea. Some of these wind parks are located more than 100 kilometers away from the coastline, so HVDC is also required for low-loss energy transfer. One of the main challenges of the use of these fluctuating renewable energy sources is storage of energy. Today, pumped storage plants provide part of the expensive balancing energy. Two possible scenarios are being discussed concerning the storage requirements of the future energy supply infrastructure based on the increasing use of renewables. Firstly, the European transcontinental supergrid distributes the electrical energy throughout Europe using efficient HVDC technology. With the integration of wind power from Northern Europe and solar power from the south, energy balancing is achieved. The vehicle-to-grid concept represents another scenario. The batteries in electric vehicles are used as decentralized distributed energy storage for the power grid. Energy management with bidirectional energy flow between the vehicle and grid demands intelligent power electronics. We are experiencing changing times from the carbon era to the age of solar power, and from an energy-consuming society to an energy efficiency society. In the all-electric society vision, sustainable electrical energy forms the basis of the energy supply. We use electrical energy efficiently in all areas of life, such as at work or home, and for mobility and leisure. The key to achieving this vision is power electronics.